Moving on to question 4 on the AP exam. This is a calorimetry kind of question, and there's a lot of information again in the paragraph and in this data table. So I'm gonna actually kind of visualize it myself first to get the idea of what's going on, and that should help us answer the questions. So I'm just gonna scroll down a little bit and draw a little diagram of what I think is happening. So I have a little calorimeter, so a coffee cup, it could be a beaker of water. And the water, if I look at my data table, there's 52.0 grams of it, and it has an initial temperature of 25 degrees Celsius, okay? So this is my water, and it's 25 degrees Celsius. And then what I'm gonna do is I'm gonna take this metal cube that I heated up to 100 Celsius, okay, so this was heated up. Then I'm gonna take this metal cube and put it in the water, okay? And then I've got a thermometer in the water. And then what I see is that after this cube goes in here, the water's temperature went up. So that means actually heat went into the water. It's actually leaving the metal cube and going into the water. And the temperature went up, which is what my thermometer is showing in the diagram in question A. So now that we understand a little bit about how that's set up, let's look at the question. What is the highest temperature of the water? Okay, this question's not too difficult. All we have to do is look at the calibration of our thermometer and the intervals. And what I see is that like 30 is here. So each tick mark is 1 degree Celsius. So 31, 32, 33, 34, 35, 36, 37, 38. And I can see that the temperature is between 38 and 39. So it's going to be 38.5 degrees Celsius. Moving on to question B, a particle level representation. So a diagram is shown below of the water molecules in the calorimeter before and after the metal cube was added. So where it says before, this is the water at 25 degrees Celsius. And then where it says after, that would be 38.5 degrees Celsius. That's kind of linked to question A. I'm going to erase what I did here. And what it says in this question is that each of these arrows, these arrows represent the speed of the water molecules. And what they want me to do in this question is draw the speed of the water molecules in the after diagram. So what I know is that the temperature went up. So each of these arrows' lengths will increase to show that they're moving faster than they were before that metal cube was added. Okay, so we will lengthen these arrows to show relatively similar to what was here to show that each water molecule shown has increased in speed. All right, question C. This one, assuming that the metal transfers 2940 joules of thermal energy to the water, calculate the specific heat capacity of the metal in joules per gram degree Celsius. So I'm being asked in this question to solve for the variable C, specific heat capacity. I'm given the variable Q, which is the 2940 joules. Now, we just have to be careful because if you remember, actually, maybe I'll draw this again. So if you remember what we had, when you put the metal ball in the water, the heat was going this way. So that means the water got warmer and therefore, so Q, I'm going to call water Q of surrounding. That is positive. It got warmer. Q of the metal, which is the system, it has to be negative because that's the law of conservation of energy, right? The transfer of energy from one object to another. So therefore, Q in this question must be negative 2940 joules, okay, because the water gained 2490 joules. And then the initial temperature was 100 degrees Celsius. And remember, I have to be careful, okay? It's the initial temperature of the metal. Okay, not the water, because like all of our variables are for the metal. So I have Q of the metal. I'm going to find the specific heat capacity of the metal. So I need the initial and final temperature of the metal. All right? So TF is 38.5. And then the mass, okay, let's go back again. Be careful, there are two masses shown in the data table. We need again the mass of the metal cube, 98.1 grams. All right, What else? Okay, so we're going to take these variables and substitute them into this formula, Q equals mc delta T, and I'm going to isolate for C. So C becomes Q over m delta T. So C is going to be negative 2940 joules divided by 98.1 grams. So notice your units, nothing will actually cancel out here. And my delta T is going to be, it's TF minus TI. So you'll get a negative number here, which makes sense because when you divide, the negative divided by negative will turn into a positive. And so my answer is 0.487 joules per gram degree Celsius. That's the specific heat capacity of my metal, and that must be a positive value. And then finally, let's move on to question D in this problem. So in the second experiment, or in a second experiment, 2940 joules of energy is transferred from 98.1 grams of aluminum. So we've changed the metal now. And aluminum has a different specific heat capacity. Explain how the magnitude of the temperature change in aluminum will compare with the temperature change of the metal in the original experiment. So we already know that metal 1, that's my original one, it had a delta T of TF minus TI. It had a delta T of, we already did it above, negative 61.5 degrees Celsius, right? And so why don't we use the data we have for the aluminum and just do the same thing? Let's try to find delta T for the aluminum and then compare. Now, if you look at the AP answer key, there's a couple ways you can solve it. I like the calculation just because it's a little bit more, it's a little bit more concrete, or I guess you could explain it in words as well, but just the numbers help me kind of visualize this a bit better. So I know for the aluminum, the Q is negative 2940, because remember it's losing energy to the water. The mass of the aluminum is 98.1 grams. And then the specific heat capacity is 0.897 joules per gram degree Celsius. So if I plug these into my Q equals mc delta T formula, let's isolate for delta T. Delta T will become Q divided by mc. And let's see what we get here. So Q is negative 2940 joules. The mass is 98.1 grams. And the specific heat capacity is 0.897 joules per gram degree Celsius. Joules will cancel out. Grams will cancel out. I'll get a delta T. It's negative 33.4 degrees Celsius. So therefore, what I can see is when I'm using aluminum, because of its specific heat capacity, this number means the amount of energy I need to raise 1 gram of aluminum, or whatever the substance is, by 1 degree Celsius. I need more energy to raise that aluminum's temperature. So it makes sense that my delta T, because they're both starting at 100 degrees Celsius, it makes sense that my delta T is actually a smaller number. Now, if you look at the AP answer key, when they did this, they took the absolute value of each of these answers. So for example, they took the absolute value of this and just said delta T of the original metal was 61.5 degrees Celsius. And if I take the absolute value of this, the delta T of the aluminum is 33.4 degrees Celsius. That makes it a little bit easier to analyze. So what we can say is that the aluminum, I'm running out of space here, the aluminum will give you a smaller delta T than the original metal. Okay, hopefully that makes sense, and we'll pause it there. You can watch the next question in the next video.